95% of the universe is completely invisible. We can't see it, touch it, or detect it with any telescope ever built. But a team at Texas A&M just built a detector so sensitive it could catch a particle that might only interact with normal matter once per decade.
Once per decade, one single interaction in 10 years. How do you even begin to design an experiment for that?
You cool your detector down to nearly absolute zero. We're talking fractions of a degree above minus 273 Celsius, and you wait. This is the story of dark matter, and the race to find the invisible architect of everything we see in the cosmos.
Okay, back up for me. Dark matter, everyone's heard the term, but what actually is it?
So here's the problem. When astronomers look at galaxies, they can calculate how much mass should be there based on all the stars, gas, and dust they can see. But when they measure how those galaxies actually move, how fast they rotate, how they pull on each other, the math doesn't work. There's way more gravitational pull than the visible matter can account for.
So something invisible is adding extra gravity?
Something massive and invisible. Fritz Zwicky first noticed this back in 1933, when he observed galaxy clusters moving too fast. Vera Rubin confirmed it in the 1970s by measuring galaxy rotation curves. The outer edges of galaxies were spinning just as fast as the inner parts, which is impossible unless there's a huge halo of invisible matter holding everything together.
That's been known for almost a century, and we still don't know what it is.
The evidence has only gotten stronger over time. Gravitational lensing, where dark matter bends light from distant galaxies, gives us maps of where dark matter is concentrated. The cosmic microwave background radiation, which is the afterglow of the Big Bang, shows patterns that only make sense if dark matter existed in the early universe. The bullet cluster, where two galaxy clusters collided, shows the visible matter and dark matter separating, direct proof that dark matter behaves differently from normal matter.
So the evidence is bulletproof. It's the identity that's unknown.
We know a lot about what it does. Dark matter makes up about 27% of the total energy content of the universe. Dark energy, which is a separate mystery entirely, accounts for about 68%. That leaves just 5% for everything we can see. Every star, every planet, every person, every atom you've ever encountered, 5%.
We are a rounding error in the universe.
A cosmic footnote, and dark matter isn't just some abstract concept floating in deep space, it's the scaffolding the universe is built on. Without dark matter, galaxies wouldn't have formed. Stars wouldn't have formed, we wouldn't exist. It acts like cosmic glue, pulling matter together into the structures we see today.
So what's the leading theory for what dark matter actually is? Like, what are we looking for?
The leading candidates for decades have been WIMPs, weakly interacting massive particles. The name tells you the problem. They're massive enough to have gravitational influence, but they interact with normal matter only through gravity and the weak nuclear force. That's why they're so hard to find.
Where did the WIMP hypothesis come from? Why do physicists think it's particles?
It comes from a beautiful coincidence called the WIMP miracle. If you take the physics of the early universe right after the Big Bang, when everything was incredibly hot and dense, and you calculate what would happen to hypothetical particles with roughly the mass of a heavy atom that interact through the weak nuclear force, you get almost the right amount of leftover matter to explain dark matter. The numbers just work out.
So the math predicts them.
The math suggests them strongly in several extensions to the standard model of particle physics, like supersymmetry, naturally produced particles with WIMP-like properties, so you have both cosmological evidence and theoretical motivation pointing in the same direction.
How weak is the interaction we're talking about?
A WIMP could pass through the entire Earth without interacting with a single atom. Billions of them might be streaming through your body right now, and you'd never know. To detect even one interaction, you need extraordinary sensitivity and extraordinary patience.
So how does super CDMs try to catch something that barely exists?
Super CDMs, that stands for Super Cryogenic Dark Matter Search, uses semiconductor detectors cooled to near absolute zero. At that temperature, the atoms in the detector are almost perfectly still, so if a dark matter particle bumps into one of those atoms, even the tiniest nudge creates a signal they can pick up.
Like a perfectly still pond where even the smallest pebble creates visible ripples.
Great analogy. And the key breakthrough from this team came back in 2014. Dr. Rupak Mahapatra and his collaborators at Texas A&M introduced something called voltage-assisted calorimetric ionization detection. The paper was published in Physical Review Letters, and it was a game changer.
What does voltage-assisted calorimetric ionization detection actually mean?
Let's break it down. When a particle hits the detector crystal, it produces two things, heat and ionization, which means it knocks electrons loose from atoms. A calorimeter measures the heat, an ionization detector measures the freed electrons. By applying a voltage bias across the crystal, they amplify that ionization signal massively. So particles that would have been invisible before suddenly become detectable.
So they're essentially turning up the volume on a whisper.
Turning up the volume on a whisper in a hurricane because the background noise in these experiments is enormous. Cosmic rays, radioactive decay in the surrounding rock, even body heat from researchers, all of it creates signals that can drown out a potential dark matter interaction. That's why these experiments run deep underground, often in converted mines, to shield them from cosmic radiation.
Where does the super CDM's detector actually live?
The next generation of super CDMs is being installed at Snow Lab in Ontario, Canada, 2 kilometers underground in a working nickel mine. That depth of rock acts as a natural shield against cosmic rays.
What does near absolute zero actually mean in practice? How cold are we talking?
About 15 millikelvin, that's 0.015 degrees above absolute zero, roughly minus 273.3 Celsius. For reference, outer space is about 2.7 Kelvin, so these detectors are almost 200 times colder than the vacuum of deep space. At that temperature, thermal vibrations in the crystal are essentially eliminated. The material becomes incredibly quiet, so even the faintest whisper of a particle interaction stands out.
Colder than space. That's wild. How does this compare to other dark matter experiments? I've heard of xenon and lux.
Great question. The big difference is in what they're looking for and how they look. Experiments like Xenon and Lux use massive tanks of liquid xenon LZ, the latest version, uses 10 metric tons of it. They're optimized for detecting heavier WIMPs, particles with masses around 10 to 1,000 times the mass of a proton.
And super CDMs goes smaller?
Much smaller, the voltage assisted technique Mahapatra pioneered allows super CDMs to search for low mass WIMPs, particles that are lighter than what xenon based experiments can see. It's a completely different corner of the search space, and that's deliberate.
Because if you only look in one place, you might miss it entirely.
Mahapatra himself said it perfectly. No single experiment will give us all the answers. We need synergy between different methods to piece together the full picture. There's also the Tesseract experiment, another project Mahapatra's team is contributing to, which pushes sensitivity even further.
So, we've been searching for dark matter for decades. Why haven't we found it yet? Is there a chance it's not actually there?
The gravitational evidence is overwhelming. We can see dark matter's effects in galaxy rotation, gravitational lensing, the cosmic microwave background radiation, and the large scale structure of the universe. It's not a matter of whether something is there, it's a matter of figuring out what it is.
Could it be something other than WIMPs?
Absolutely. There are other candidates: axions, sterile neutrinos, primordial black holes. Some physicists think dark matter might be a family of particles rather than just one. The search is broad precisely because we don't know the answer yet.
What would it mean if we actually detected a dark matter particle? Like, why does this matter for regular people?
It would be one of the biggest discoveries in the history of physics, comparable to discovering the electron or the Higgs boson. It would open an entirely new chapter in our understanding of the universe. The standard model of particle physics, our best description of how the universe works at the subatomic level, has no explanation for dark matter. Finding it would require new physics.
New physics, meaning new theories, new mathematics?
And potentially new technologies we can't even imagine. As Mahapatra put it, if we can detect dark matter, we'll open a new chapter in physics. The search needs extremely sensitive sensing technologies, and it could lead to technologies we can't even imagine today. The detector technology being developed for dark matter searches already has applications in quantum computing, medical imaging, and materials science.
So even if we don't find dark matter tomorrow, the search itself is producing useful technology.
The journey matters as much as the destination, and the Texas A&M team's work was recently featured in Applied Physics Letters, which underscores how the detector innovations have value beyond just dark matter.
So to sum this up, minus 95% of the universe is invisible. Something massive is holding galaxies together. And right now, deep underground detectors cooled to near absolute zero are waiting for a particle that might show up once in a decade.
And thanks to innovations like voltage-assisted calorimetric ionization detection, we can now search corners of the particle landscape that were completely out of reach before. We're getting closer. The invisible architect of the universe left fingerprints everywhere. We just need the right tools to read them.
Let me push back on something. We've been looking for WIMPs for decades now. Experiment after experiment has come up empty. At what point do scientists start thinking WIMPs don't exist?
It's a legitimate concern, and some physicists are already shifting their focus. But here's the thing. Each null result isn't a failure. It's a measurement. Every time an experiment doesn't find a WIMP in a certain mass range, it tells us where dark matter isn't. That narrows the search space.
So you're ruling out possibilities rather than finding the answer directly.
Think of it like searching a massive building room by room. You haven't found what you're looking for yet, but every empty room means fewer rooms left to check. And the voltage-assisted technique from Texas A&M opened an entirely new wing of the building that nobody could access before.
How long could this search realistically take?
It could happen tomorrow if we get lucky, or it could take another decade or more. The next generation of super CDMs at Snow Lab should start taking data soon, and it'll be the most sensitive low-mass dark matter search ever conducted. Meanwhile, the LZ experiment in South Dakota is running the most sensitive high-mass search.
It's like casting two nets in different parts of the ocean.
And axion experiments like ADMX at the University of Washington are casting a third net for a completely different type of particle. The field has never been more active or more diverse in its approaches.
There's something almost philosophical about searching for something that makes up most of the universe but refuses to be seen.
Mahapatra used a great analogy. He compared it to the parable of blind men touching an elephant. We're touching the tail and trying to describe the whole animal. We know something massive and complex is there. Dark matter shapes every galaxy, every cluster, every large-scale structure in the cosmos. It determined where matter clumped together after the Big Bang, which determined where stars formed, which determined where planets formed.
Which determined where we formed.
We owe our existence to dark matter, we just can't see it, yet.
Fingerprints everywhere. And we're finally building the magnifying glass.